So just like with single variable, the first derivative test in multivariate calculus just checks first derivatives and sees if they're equal to 0. So it has basically the same form. For a function to have a local minimum or a local maximum, we have to be at a critical point. The gradient vector grad f or df has to be 0. Or said another way, we need all of the partial derivatives of our function to be equal to 0. Because if the partial derivatives aren't equal to 0, the gradient is non-zero, then that means that there's a direction, the direction of the gradient vector, where we could go to make the function a little bit bigger, or we could go in the opposite direction to make the function a little bit smaller. So if the gradient isn't 0, there's no way we're at a local min or a local max. So for example, here's a function of two variables. F of xy is x to the fourth minus 2x squared plus y squared. Here's its gradient vector. The gradient is the x partial derivative is 4x cubed minus 4x, and the y partial derivative is 2y. So to be at a critical point, to have a local max or a local min, we'd need both of those partial derivatives to be equal to 0, not just adding them together or anything like that. So we would have to have 2y equal to 0. That forces y equal to 0. And we'd also have to have 4x cubed minus 4x is equal to 0. That says that x cubed minus x is equal to 0 because I can divide by 4. And then I can factor the left-hand side. The left-hand side factors into x times x squared minus 1 is equal to 0. And then I also know how to factor x squared minus 1. That's x plus 1 times x minus 1. And so I know that y is equal to 0. For this to be equal to 0, I need x equals 0 or x equals minus 1 or x equals plus 1. So there are actually 3 different critical points where all of the partial derivatives vanish. One of them is when x is 0, y is 0. One of them is when x is minus 1 and y is 0. And one of them is when x is plus 1 and y is 0. 3 critical points for this function. Depending on exactly what the function looks like, you may get more or less critical points, and it can be a lot more tricky to figure out exactly how the set of solutions is. There's no step-by-step way to solve these because they're not solving systems of linear equations like we were before. But now, even after we've done that, once we find a critical point for a function, the function can actually behave in some ways that are a little bit exotic compared to what happens with single variable calculus. So if we're at a critical point, we could be at a local maximum. So imagine this is the graph of a function of 2 variables. A local max would kind of look like we have a cap near there. So everywhere nearby, the function gets smaller. Or we could have a local minimum where the graph kind of curves upward nearby and every value of the function nearby is bigger. Or we could have this situation where in one direction the function curves upward and in the other direction the function curves downward, like this. So this kind of thing is often called a saddle point because its picture or the graph of it tends to look like this. This is neither a local min nor a local max. And as a result of this, we get slightly different behavior for the second derivative test.